In this podcast, you're going to learn about the derivative function to sine x and the derivative function to the cosine of x. We're going to begin our investigation with a dynamic sketch, meaning that you're going to see the sine function graphed using technology, and then you're also going to see the graph of its derivative being graphed um, at the same time. So I'm just going to click on this link here, and it's going to take us to a Geometry Sketchpad file. And this particular file, I'm going to select, let's see, we want the sine curve in radians as well as its derivative. So what you can see is the graph of y equals sine x, or f at x equals sine x. The equation at the top, okay, that you can see here, so this equation here, the 1, of course, is the amplitude, okay? This parameter here, otherwise known as b, is the horizontal stretch and or compression factor. So for the base function sine of x, we recall that both the amplitude and also this factor are equal to 1. The 0, of course, is the phase shift. So that is the horizontal shift, either left and or right. So it's set to 0 for the base curve. And then over here, we have the vertical translation constant. It is set 0 for the base curve. Notice also that here in the equation, I can't necessarily highlight that here in Geometry Sketchpad, but I can definitely circle it using the mouse. So this term right in here, okay, so we have the independent variable x, which represents the angle in in radians, and c is the power of x. Okay, and in this case, the c value we're going to denote as 1 for the base curve. When we get into other derivatives of trig functions, then the degree of that term will increase to 2 and or 3. Okay, other things that you should be aware of is this here, the gradient of the sine function. So the gradient simply means the slope of the sine function. So if you take a look at this with me, at a value of pi, which is here, if you can see that highlighting or not, we can see that the instantaneous rate of change of y versus x, slope of the tangent at that particular value of 3.3949 is minus 0.9881. Okay, so the slope of the tangent is roughly -1 at x equals 3.4. So what we're going to do, or what this dynamic sketch will do, is we're going to plot the gradient function, the slope function, or the derivative function to the sine function. Okay, so the independent variable will be x, whereas the value that gets plotted for the independent variable will be the slope, or the gradient of the sine function. So let me hit the animation button here, and let's just kind of see what happens. Now it seems to be going beyond the domain. Oh, and let's see, here it comes back now. Okay, so it's moving in from right to left as opposed to left to right, which would be ideal, but this is fine. Okay, so it will come back. Here we go. Okay, so for each value of x, the corresponding y value is the slope and or the gradient of the function. So let's bring it back here to highlight that. So if I stop it here, okay, at this particular point, P, okay, at this point of tangency, if you look at the tangent, okay, and you were to calculate its slope, the slope of that is highlighted in the table, so it's 0.4. So when x at this point here. So at these 2 points, x is equal to 1.1. Okay? The slope of the function, or the slope of the tangent, is 0.4. So what is being mapped out or plotted on this new curve? As you can see here, the y value of this point is approximately 0.4. It is the gradient or slope of the tangent at an x value here of 1.176. Okay? So if you look closely at the graph or the resulting graph, okay, that is the one that is in bold face font, in purple, the thickened curve, you might recognize that as a specific sinusoidal function. In fact, it is none other than the cosine curve. So what we're seeing from the dynamic sketch is that the derivative of the sine function, the derivative of sine x, with respect to x, is none other than cos x. Okay? So later on, what we need to do also is, we could, using technology, show the derivative of cosine as being related to the sine function. But we're going to use first principles to prove that that definition is true, and then we'll use that definition to our advantage in terms of helping us with other derivatives. So let's start out with this one here in part B. Let's do a first principles proof. So I do need you to recall that the slope of the tangent, the instantaneous rate of change at a particular value of x for a function, is given as the limit as h approaches 0 of the function at the value f at x plus h minus f at x all over h. So we're going to apply that definition to the sine function. So let's let f at x be sine x. So what we'll do is we'll then take this expression, okay? So that is to say, the derivative of y with respect to x is going to be the limit as x approaches, h, get our variables mixed up here, h approaches 0. So what we'll have here, f at x plus h is going to end up being the sine of x plus h minus f at x, which is sine x, all over h. Now recall that the goal of first principles proof is to somehow remove a discontinuity. So we can't have this here in the denominator, otherwise the expression is undefined. So there must be some kind of work that we can do in the numerator. Okay, specifically this term is going to need some attention in the numerator that will allow us to find the derivative. So what I would like you to do is I now need you to recall, right, a particular rule. Okay, think of the sine of x plus h as being equivalent to the addition formula for sine. Okay, so you might remember the compound angle formula, or the addition formula, sine a plus b. So it's equivalent to that. So remember that sine a plus b, right, was the sine of a times the cos of b plus the cos of a times the sine of b. So with that formula for the sine of x plus h, come on back, and that's equivalent to then sine of x times the cos of h plus the cos of x times the sine of h. So with that being established, we can take this and bring it back into that formula there. So let's continue working on this derivative. So dy by dx is the limit as h approaches 0 of, let's substitute this expression in here, sine x cos h plus cos x sine h minus sine x all over h. Okay? So now that we're at this point, what we need to do is we need to somehow group the terms so that we can work with removing any discontinuities. So why don't we consider doing the following? Let's take this expression, and what I would like to do, or at least have us do, is to group the terms for their likeness, for their parts that are alike. So if we look at sine of x here, we have sine of x here. So it would stand for us to reason that we could regroup the terms as such. So I'm going to group those two together, and then I'm going to leave the other term here on the end. And the nice thing about that is that we can factor out a sine x. So let's factor out a sine x here. Okay, pull that sine x out. And what that means is we have cosine of h minus 1 left on the inside, plus, I'm just going to change colors here, plus the cosine, and I'll explain why in a moment, plus the cosine of x times the sine of h, all over h. Okay, so far so good. What we're going to do now is we're only going to focus on the parts that involve or incorporate an h into their definition. So remember that there are particular limit properties. So the limit properties tell us that due to this addition, okay, that we have here, we can split this particular expression into two fractions. So the sine of x times the cos of h minus 1 over h plus the limit as x approaches. Oops, should be, here I'm writing x's down when they should all be h's. So tends to be a habit of mine to always have x being written down. Let me fix that. Same thing here. I'll repair that quickly. Good. Okay. And over here, the limit as h approaches 0 of the remaining term. So cos x sine h all over h. Now the interesting thing about the terms that were color-coded in orange, okay, color-coded in orange, is that as h approaches 0, these values here, okay, are going to remain constant. Okay, they do not depend on the value of h whatsoever, right? H has no effect on those values. So what we can do is we can pull those values out front of the limits. So I'm just going to rewrite this expression, keep our colors here. So we're going to pull those out front. And what we're left with here is the cos of h minus 1 all over h. And over here, what we're left with is the limit as h approaches 0 of sine h over h. Now that we're at this point, okay, take note, okay, take strong notice that graphically, right, it was shown with the dynamic sketch that the derivative of sine x was cos x. So what that means for us is that ultimately we would love to see this term here, we would love to see that being equal to and or equivalent to 0, and we would love to see this being equivalent to 1, right? So what we need to do is to find some form of proof that is going to establish that those two limits are both 0 and 1 respectively. Well, there is a bit of work involved here. So in order to help you establish those proofs or those identities, what you can do, this is a little over and above what we're doing here, but if you were to go to my YouTube channel, I did add to the favorites list proof, and there's a number of them out there, and it's a good proof to know because you're going to see it next year in your calculus course. So let's head to the YouTube channel. We're having a bit of a connection problem, and we're going to end up doing a login here. Okay, so I would have to log in. Let's not take the time in order to do that right now. Okay, but you are going to see a proof of that. Let me go ahead a page here. I'll just show you one particular idea. Okay, in essence, when you watch the video back, what the author or the presenter is showing is something known as the Squeeze Theorem. Okay, and what that means is that, let's say for instance that we have three functions. We have f, we have g, and we have h. Let's just say for the sake of argument that the value of f at an x is less than g and is less than h. Okay, let's insert sine of x over x here, which is sine of h over h. Okay, what's going to be shown through the video clip, that is if you have an interest in seeing how this works, is that there is an expression that the author develops. Okay, and in fact the expression they develop, and you'd have to watch it to see the proof. Okay, you'd have to watch it to see that, is that they end up establishing that their h at x, their function that they are using in their proof, is equal to 1. They also show that f at x is equal to 1. So what that means, or what this implies, is that because sine of x over x is sandwiched or squeezed between two values that are the same, it means that the sine of x over x is also equal to 1. Okay? So if you into this stuff, please do watch that video. It's about 18 minutes. You can take and leave certain parts of it, but it is relatively good. Another proof, in the event that you need it, is for this one here. So you're going to see that also at the course website. So I'll take you back. There is a document on the Unit 4 subpage, okay, right here, that shows a proof. That is this one, shows a proof of that particular theorem. Okay, here it's going to take moments for it to adjust, but again, please do access that, and then you'll be able to see a proof for that. So in terms of finishing our proof, what we're going to do is we're simply going to state that this would be equal to sine x multiplied by 0 plus the cos of x times 1 which at the end of the day is going to give you the cosine of x. And that's due to the fact, right? Since the limit as h approaches 0 of cos h minus 1 over h equals 0, and also due to the fact that the limit as h approaches 0 of sine h over h is also equal to 1. So in conclusion, we can see that the derivative of the sine function with respect to x is none other than the cosine of x. Okay, so this video is running about 20 minutes. We're going to stop this one. There is one more I do need to share with you with regards to the cosine function plus one example.